So if you take a look at this worksheet, you have a bunch of square roots you need to simplify. The first one, the square root of 16, you end up with 2 times 2 times 2 times 2. So you have two groups of 2's, which gives you 4, or you could just say the square root of 16 is 4. For 24, you should have gotten 2 times 2 times 2 times 3. Can you bring anything out? A set of 2's, which gives me 2 root 6. For the next one, you have 3 times 3 times 5, which is 3 root 5, but there's a negative, so you also need an I. Anytime you square root a negative, you get an I. What other roots create I's? 4, 6, 8, all the evens. So if it is the square root of negative something, that's going to create an I. But if it's the third root of negative, what do? You just put negative out front. So if this number is even, you get an I. If that number is odd, the negative just comes out. All right, for 48, what did you get? 4. I had 2 times 2 times 2 times 2 times 3. Is that what you guys got? So it should be 4 root 3. Okay? I don't know. I don't think that far ahead. All right, 42. What do you get when you factor 42? 2 times 3 times 7. Do we have any sets, any groups? No. So this one, it's not prime, but it's already simplified. It's sort of like saying simplify 3/7. Okay, done. It doesn't go any further than that. All right, what about 180? Yeah, the answer is root 42. It doesn't go any further than that. Unless you multiplied wrong, what did you get? Right. So 2 times 3 times 7, what can I bring out? Nothing. There are no sets. So you can't write anything on the outside. There are no perfect squares inside there. Okay, 180 is 2 times 2 times 3 times 3 times 5. So I can bring out a set of 2's and a set of 3's, which makes 6 and I root 5. Okay, so let's skip down. I think you guys got the hang of this. Skip down to negative 108. That's 2 times 2 times 3 times 3 times 3. What can I bring out? Set of 2's and a set of 3's, so that would be 6. If I look at my x to the 4th, that's 2 groups, x squared. If I look at the z to the 3rd, that's 1 group, and I need an I, and square root what's left? 3, no x's, and a z. So notice the I goes behind the numbers, behind the variables, but before the square root. Okay? And let's do the last one. So when I factored it, I got 2 times 3 times 3 times 3 times 5 times 5. So what you got? What can I bring out? Set of 5's and a set of 3's. So 15. How many A's? None. How many B's? None. How many C's? Wait, sorry, what? Where are you confused, Abby? $20 and $10? We're on this one. Yes, 20 and 10 is correct for 200. So it's 135 and 10, which would be, so this is 2 and 5. So that would be 5 and, oh, did you mess up the 10? Did you put 5 plus 5? Oh, yeah, that'll mess you up. So 15 c to the 6th I root, we have a 2 and a 3 left over, so 6 a b, and all the c's are gone. You know, I think that all the time. Okay, so let's look at these two quadratics, and let's use the box to factor them. So for the first one, I draw the box, I stick in x squared and 9. Multiply those together, I get 9x squared. I'm looking for the factors of 9 that add to be -6. Is there a set that does that? Close. -3 and -3. So that's going to give me x, -3, -3. So my factors are x minus 3 and x minus 3. Now, you kind of did a little bit of this last week. What are the roots? Just 3. Right? It's actually 3 twice. So if you look at this graph, no, this is not plus or minus. This looks like that. It's not a difference of squares. If we were graphing x squared minus 9, that would be x minus 3 and x plus 3. But that's not what we have here. We have x minus 3 and x minus 3, which creates a duplicate root, which means the graph just comes down and bounces off the axis. Okay? So whenever you have a duplicate root, your factors are going to be the same, and your quadratic is going to have this special property that we talked about last week. Okay? All right, let's do the next one. So x squared and 36, multiply those, 36x squared. Are there factors of 36 that add to be 12? 6x and 6x, and the same thing happened. X, plus 6, and plus 6. So what are the roots? There's only one root, it's -6, and it happens twice. So the roots here are x equals 3, and the root here is x equals -6. So the first question, what's special about these quadratics? It only has one root, and you could call it a duplicate root. Sometimes we use the word it has multiplicity of 2, meaning it's the same root happens twice. You could have the same root with a multiplicity of 3 or 4 or 5 or whatever you want. Okay? Multiplicity. Don't worry about it. Next year we'll talk about multiplicity. Oh, does it really? Oh, yeah. Sorry. Yeah, we're not going to say multiplicity, but so this question, what do we call a quadratic that only has one root? It's called a perfect square trinomial. That's different from saying it's a difference of squares. If the same root happens twice, it's called a perfect square trinomial. Okay, the next question. What does a quadratic that has only one root look like? Right, it only touches the x-axis once, and I like the term it bounces off the x-axis. If that root happens twice, then the graph bounces off the x-axis. Yes, the alternate method. So normally we use the box, we get x minus 3, and then how do we solve that? We set them both equal to 0. And that works, but there's another way to do this. Okay? If these are the same factors, is there a way to combine those two factors into one? Can we write them as one factor instead of two? But you do this. You do x minus 3, x minus 3 squared. Now, the only reason we're allowed to do that is because they are the same factor. If it was x minus 3 and x plus 3, can I combine them into a single factor? No, because they're two different numbers. Now, if I set that equal to 0, can I solve that? Or rather, how do I solve that? Well, how do you undo a second power? Take the square root. So I get x minus 3 equals, what's the rule we learned last week whenever you square root an x squared? That's what you tried to do earlier, Sam. Nope. So if I had x squared equals 49 and I took the square root, I got x equals, no, plus or minus 7. Whenever you square root an x squared, there are actually two answers. So in this case, it's plus or minus, what's the square root of 0? 0. What times itself is 0? 0. So plus or minus 0 is actually just 0. So I get x minus 3 equals 0, and I add 3. Yes. So you might say, why would I make it harder? Because we're about to use this property to solve equations that we could never solve before. So let me show you again how it works. Over here we get x plus 6 squared equals 0. So I take the square root. How am I getting what? Up here we had x plus 6 and x plus 6. Yeah, it's the same problem. Oh, poor Abby. So I square root x plus 6 equals, it's plus or minus 0 again, but do I need to worry about the plus or minus? No, equals 0, and then subtract 6 and subtract 6. Now, I would never solve it this way. If it factors, you might as well just factor it and set each factor equal to 0. But what if it doesn't factor? And that's where we're headed today. So turn the page. Yes. I was just showing you another way to do it. Hang on, Abby. It'll be okay. Okay. So create a one-root quadratic with x equals 8. So what would the two factors be? X minus 8 and x minus 8. Now if I multiply those together, no, let's stick it in the box. Oops. X minus 8, so x squared, negative 8x, and 64. Do those 8's cancel? No. So we get x squared minus 16x plus 64. Now this is the relationship that I told you about last week. What do you notice about the middle term? And this is the answer for this question. How does the middle term compare to the number in the factor? It's twice as big. So the middle term is twice as big as the factor. Write that down. The middle term is twice as big as the factors. What about the last term? It's that factor times itself. So the last term is the factor squared. And we're going to use that relationship to solve problems that we couldn't solve before. What? Now what? We haven't done anything yet. Okay, now I'm going to teach you how to solve it. So I look at x squared minus 8x minus 20. Is that a perfect square trinomial? Is it going to factor into something twice? No. Does it touch the x-axis just once? No. How do you know it doesn't? The n number has to be a perfect square. Is 20 a perfect square? No. So this particular quadratic does not do the bounce off. Okay? So what we're going to do is we're going to change it into a perfect square. We're going to alter the equation so that it is a perfect square and then solve it. And yeah, somewhere along those lines. The trouble is this 20 is the wrong number, right? 20 is not a perfect square. And even if it was the perfect square, it would have to be the correct perfect square, because there's only one of them that will work. All other perfect squares will be incorrect. So what we're going to do first is we're going to move that 20 to the other side. So how do we move negative 20 to the other side? Add it. So write it like this. X squared minus 8x, leave a gap, equals 20. Because we're going to fill in the number we want. There's one number that we're looking for. And that number has the same relationship as all other perfect square trinomials. So instead of factoring like this into two different factors, I want it to factor into something to the second. Okay? So we need to figure out what that something is. Well, what's the relationship between a factor and the middle term? It's twice as big. Well, the middle term is twice as big. So in the factor, we'll have x minus, how do I know it's minus? The middle term is negative, and the factor has to be half as big as the middle term, 4. Okay? So if I want to create a perfect square, the only way it will work is if this term in the factor is half as big as the middle term. Well, if this number is negative 4, what will the number here be? Positive 16. Now, will this bounce off the x-axis? Yes. But we have a 20 hanging out on the other side, which totally changes the graph. And the other problem is, I just added 16 pounds to the right side of this equation. So it used to be perfectly balanced, and now it's unbalanced. How can I rebalance it again? Add 16 to the other side. So I can add 16 pounds to one side of my balance, as long as I add 16 pounds to the other side. So now I get this equals 36. Okay? Now, we're used to that 36 being a 0. And if that 36 is a 0, that means that there's only one root. But we already know that there are two roots. So we can use this method to find out what they are. We take the square root, and we take the square root, and I get x minus 4 equals, not 6, plus or minus 6. we square rooted an x squared, so we get plus or minus 6, and now I add 4, and this is a little tricky, plus or minus 6 plus 4. So x equals 6 plus 4 is 10, and negative 6 plus 4 is negative 2. Now, if we look back to the original would have factored into x minus 10 and x plus 2, because negative 10 times 2 is negative 20, and negative 10 plus 2 is negative 8. Good question. Why would we do the hard way to solve something we already know how to do the easy way? And my answer is you wouldn't. For that particular problem, I would factor it. But we're going to run into problems that don't factor, and this little trick we did here will still work. So we're going to practice the trick on easy problems that we could have done the other way until we run into more difficult problems. Okay, so we're practicing on the easy stuff so that we can learn how to do the harder things. But yeah, if you were to have this problem, just factor it. If you try to factor something and it doesn't work, then you can try this other method that we're using. So, this problem here, is it a perfect square trinomial? No, it's not. So, let's make it a perfect square. And this is called completing the square. So I move the 45 over, x squared plus 12x, leave a space, equals negative 45. And then I just do the same thing that you did last week. What number goes here? What number will complete the square? Well, we take x plus 6, because 6 is half of 12 squared. Well, if this number is 6, what number goes there? 36. Can I just randomly add 36 to one side of the equation? I need to add 36 to the other side. And what is negative 45 plus 36? So that equals negative 9. Okay, now what? Square root. X plus 6 equals, so we need a plus or minus because we square rooted an x squared. What is the square root of 9? 3. What's the square root of negative? I. Now what? Subtract 6, so I'm going to subtract 6. Does 3i and 6 mix? No, and we always write the real number first and the imaginary number second. So I get x equals negative 6 plus or minus 3i. No, it's still 2. Negative 6 plus 3i, that's one root. Negative 6 minus 3i, that's the other root. So it's an x squared equation. It can only have two roots. Well, if my roots are imaginary, what do you know about the graph? It doesn't touch, and if you want to know where it would touch, if we flipped it upside down, what is negative 6 plus or minus 3? Well, negative 6 plus 3 would be negative 3, and negative 6 minus 3 would be negative 9. So if you turn the graph upside down, it would hit there, which means that the real graph is up there. Now watch what happens if we try to factor this. Stick it in the box, x squared, 45, 45x squared. Are there factors of 45 that add to be 12? 1 and 45, that doesn't work. 2 doesn't go in. 3 and 15, or 5 and 9. Do any of those make a positive 12? 15 minus 3 would make 12, but it wouldn't make positive 45. So this one has no factorable answer. But if we complete the square, we find out the roots are imaginary. Not every time. So if she asked, if we try to factor it and it doesn't work, does that mean that it's imaginary? Not really. if you had this graph and it hit at really nice numbers, what if we moved it up just a little tiny bit? It will still have roots, they just won't be very nice roots. No, it has roots. These are the roots right here. If you try to factor it and it doesn't factor, it still has roots. Every quadratic has 2 roots. And you can use this method to figure out what they are. Even if they're horrible answers, you can still use this to figure out what they are. Okay. Well, imaginary roots don't really have a lot of, and it's kind of a sad thing. When are you going to use imaginary roots? Never. Do imaginary roots have bearings somewhere? Yes. But I don't really have a good response to when you're going to, I mean, I never use them. But like electronics and really advanced calculus and trig uses them. So are you ever going to use them? No. Sorry. But I mean, when are you going to factor quadratics anyway? I never do. Okay. So take a look at the next problem. What should we do with the next problem? Divide it by 2. Do I need to keep the 2? Well, you got to look at the problem, at the instructions. Solve the quadratics by completing the square, which means find the roots. If we're finding the roots, do we need the 2? No. So x squared plus 8x plus 8 equals 0. If we're factoring, we need to hang on to that 2 because it's still part of the equation. So essentially what we've done is altered the graph. So I took the original graph, which was really steep, and I made it less steep, but the roots remain unchanged. Okay? So is this a perfect square trinomial? No. So I move the 8 to the other side. X squared plus 8x equals negative 8. And I'm looking for what number will make it a perfect square. Well, I write my factor to the second. What will the factor be? X plus 4. So I've changed the quadratic that did not have a duplicate root into one that did have a duplicate root. And now, what number goes in this empty space? Plus 16. Now, am I allowed to add 16 to one side? Yes, as long as I add it to the other side. So now I get an 8 over here. Now what? Square root, and I get x plus 4 equals, don't forget the plus or minus. Now, does 8 square root? No, but 8 does factor into 2 times 2 times 2. Can I simplify that? Pull out one set of 2's. So I pull out one set. 2 root, the leftover is 2. So see all these things I've been making you do? They all have a purpose. Okay, now I need to move the 4 over. How do you move the 4 over? Subtract it, and we always write the numbers in front of the square roots, not behind. So it's going to be negative 4 plus or minus 2 root 2. Does this graph hit the x-axis? Yes, how do you know? They're real numbers. Does it hit the x-axis in a very nice place? No. If I tried to factor the original quadratic, so I get x squared times 8, 8x squared, are there factors of 8 that add to be 8? 1 and 8 would make 9. So this one did not factor. So a week ago, if I would have told you to find the roots, you would have said this is prime. But it still has roots. You just can't factor them to find the roots. which is why you need to do this trick, and you see the roots are not very nice numbers. Yeah.